Today we're going to take a look at applications of logarithms, and basically I just have a whole bunch of word problems for us to look at and hopefully give you a good feel for how these applications look when you change them into equations. And as we're taking a look at these, obviously they don't look exactly alike from question to question, but hopefully you'll get a feel for how they are alike and how to create these equations yourself. So here's our first example. A principal of $3,000 was invested at 8.25% compounded annually. How many years before the account will have $9,000? We're going to round to the smallest whole number of years. Okay, so we've seen this equation before. It looked like this: A equals P times 1 plus R over N to the NT. And remember, P is the principal; it's how much you invest. A is the amount that you want at a given point in the future. So in this case, A is 9,000 and P is 3,000. R is your interest rate, and that's 8.25 here, but you have to write it as a decimal, so 0.825. And N is the number of times it compounds in a year, so that's number is 1 for us because it said compounded annually. And then T is the time in years that we don't know. So T is what we're solving for here. So this is how this one's different than when we had encountered this before, because now we have at our disposal logarithms where we can actually pull the T out of the exponent. So here's the catch before we can continue in this problem. We need for this to actually have just the exponential part, like just this part, alone on the side, which means we first have to get the 3,000 to the other side. So we're going to divide. We're going to divide each side by 3,000. Of course, the whole point is that it cancels from the right-hand side. 9,000 divided by 3,000 is just 3. And then on the right-hand side, if we want, we can go ahead and clean up this bit, simplify this. It is a pretty simple one because of the division by 1, so this would just be 1.0825. And 1t makes it t as the exponent. So once we get it into this form, we're actually able to use either logs or natural logs. Totally your pick, doesn't matter. I think I'm just going to use natural logs throughout the whole presentation today, but if you choose to use logs, you'll get the same answers. So I'm going to use natural log 3 equals natural log of 1.0825 to the t. And of course, properties of logs say now that the t can come down in front. So this is the natural log of 3 equals t natural log of 1.0825. And to solve for t, I would need to divide by the natural log of 1.0825. And you'll need your calculator, of course, to do that. So the t, the time that we get, tells us that it's the smallest whole number of years. So let's figure out what it actually says, like decimal-wise, in the calculator and see how we answer that question. So mine tells me that it's 13.858. So clearly this is more than 13 years, less than 14 years, but it wants us to round to the smallest whole number of years. That doesn't mean round it to 13. That's 13 as a number, because in 13 years it still won't be worth 9,000. The smallest whole number of years before it's actually worth the full 9,000 and a little bit more would actually be 14 years for this problem. So this is 14 years that it takes before we reach $9,000. Okay, let's try another one. A computer. A computer is purchased for $3,900. Each year it loses 80% of the value from the previous year. After how many years will it be worth $1,000 or less? All right, so taking a look at this one, to start with, I have a typo on my screen. I was double checking that actually just a second ago. This one actually was supposed to say 20% is what it loses, 20% of its value from the previous year. So, all right, so let's take a look then. So our computer is actually originally costing us $39. We can actually talk about this just like we would talk about money. A equals P, 1 plus R over N to the NT, kind of an idea. It won't fit this perfectly, but it's the same idea. The A is the amount that we want it or expect it to be worth later on. That's the $1,000. P is the amount it's worth at the beginning. That's our $3,900. Okay, so now here's the deal. This part of the equation talks about how the investment is changing. So when we did this over here, right, it was increasing 0.0925 every year. But for us right now, it's not increasing, it's actually decreasing, and it's decreasing 20%, right? So 20% would be 0.20 every year. So it feels a little bit different because it's decreasing, but it has the same idea as the other one did. It's happening every year, so n is 1, and the t is what we're looking for. All right, so just like we had talked about on the previous problem, I need to have that 3,900 moved. So I can start by putting the 3,900, or I can divide by the 3,900. So of course this is canceling. You could even cancel the zeros over here if you would like. So you end up getting 10 over 39 on the left. And we could actually simplify. The 1 minus the 0.2 would actually be 0.8 to the t. Okay? And then, like on the previous problem, we can take a natural log on both sides. Natural log of 10 over 39 equals the natural log of 0.8 to the t. And the reason we did that, of course, is so we can pull the t down in front. So this is the natural log of 10 over 39 equals t natural log 0.8. And we're then able to divide by the natural log of 0.8. So t is equal to the natural log of 10 over 39 divided by the natural log of 0.8. And t will end up being 6.099, and it would be years, right? So if we're following the same advice, and I believe that in your notes it will tell you, or your homeworks it will tell you each time, the smallest whole number of years, or round to the nearest tenth, or whatever, we'll just use the same directions as the previous problem. The smallest whole number of years, this would actually end up being 7 years. It will take 7 years before the value of the computer is actually $1,000 or less. Okay. Let's take a look at Miguel. Miguel places a bottle of water inside a cooler. You've probably done that before. It's really cold in the cooler. Its temperature we're going to use is given in degrees Celsius. And it follows the formula. So this one's really nice because they actually gave you the formula, right? C of t equals 5 plus 17e to the negative 0.04t. Okay, cool. And the question is, after how many, this is after t minutes of time that it's in the cooler, how long before Miguel's water is 17 degrees? So 17 degrees is our goal. It's the final outcome that we want. So it's what's on the left-hand side. And then we can solve the part that's on the right-hand side and simplify. Again, we need to have all of the pieces, which would be this piece, this exponential, alone. That 5 has to move, that 17 has to move, but they need to move properly, right? So the first thing I'll do is I'll subtract the 5. So that's 12 equals 17e to the negative 0.04t, and then we divide by the 17. All right, so at this point we can take the natural log, and natural log here is actually really friendly because it is a base e problem, right? So I have natural log of e to the negative 0.04t. And one of our properties of logs say that if you have the base and the log matching in its base, that this actually cancels one another out. They're inverse operations, and we get 0.04t, the exponent itself, as the value. So we end up with natural log of 12 over 17 equals negative 0.04. And we would divide both sides by negative 0.04. If I do this, I will find that my t rounded to the nearest tenth. That's what I meant to type in there, my bad. So round to the nearest tenth. And of course, tenth means 1 decimal. So rounded to the nearest tenth, this actually ends up giving me 8.7 minutes. So he doesn't have to wait very long for his drink to cool down. Okay, so all of the compound interest we've talked about so far is compounding at a specific time interval, like compounding yearly or compounding monthly or compounding, they use the word annually, not usually yearly, but it's compounding at the specific interval amounts, right? And this one actually didn't, but they actually gave you the formula. The next one, however, we need to talk about where in the world this E is coming from in terms of creating these formulas. What is going on? And it actually comes from the idea of something happening continuously. So it's continuous interest, continuous compoundings, continuous growth, continuous decay. The key word is continuous, and it follows this particular formula, A equals PE to the RT. Now, most of that's very familiar. We've seen that before. A is the amount after time t. P is the amount initially. R is the interest rate, or the rate. I'm just going to say rate, because on some of ours we're not going to be looking at interest. We're actually going to be looking at like growth and decay of bacteria and things like that. So this is the rate as a number, and that's a number symbol. That is not a hashtag. I know you think it is, but it isn't. And then T is the time. So when we're dealing with money, the time is typically time in years, but in certain science experiments, the time might be measured in minutes or seconds or something like that. So it kind of just depends on the context of the problem. All right, so our first example actually is going to be money. So here's our example. $3,500 is invested at 4.5% compounded continuously. Find the amount present after 5 years. So our basic formula looks like this. A, the amount is what we're looking for. The principal is the $3,500 we start with. And then the interest rate is 0.045. And we also even know that it's for 5 years. So this one's actually really friendly. It's just plugging the values into one side of the equation. Your calculator gives you the answer, and we end up having, at the all said and done point of this particular experiment, if you will, $4,383.17. So we're going to use this basic framework and do a couple of other questions with it. Part B wants to know how long before the value is $10,000. This could be a standalone problem, right? All these parts A, B, and C are just kind of using on some of the initial setup part. They're not really related questions specifically. How long before the value is 10,000? So on this problem, we don't know that T is 5, right? That's the whole point, is that after 5 years, it's worth $4,300, and we want to know how long would it take for it to get to 10,000 bucks. So I have $10,000. It equals the 3,500. E to the 0.045, but it's T this time that I do not know. So this problem actually feels a lot like the one over here, right? I have E and I need to simplify things to get the E part by itself. I need all of this isolated. So the first thing we'll do is we'll divide by the 3,500. Okay, so honestly we divide by that P value almost all the time. Depends, of course, on what we're solving for, but we're solving for exponents. We do divide by it a lot. So I could actually simplify this just a little bit, just for the sake of writing it down. I could cancel out the last two zeros. This is 100 over 35 equals E to the 0.045t. Natural logs again, super nice to use because I have a base E. So natural log of 100 over 35 equals the natural log of E to the 0.045t. Now, natural log of E, right, this is canceling, so I'm left with a 0.045t. So I have natural log 100 over 35 equals 0.045t. And if I divide by the 0.045, then t equals natural log 100 over 35 divided by 0.045. Okay, I think I got it transposed right. And that will end up giving us an amount of time. Now this time is in years, right? You see this up here, time in years. And it's appropriate to measure the years in any particular way. Your book will actually, not your book, but your problems will actually say how they want this measured. So we're going to go with nearest tenth here as well. And so I'm not worried about your book telling you. This is just me not having typed it into all of our problems on our slides. I apologize for that. So if I round this to the nearest tenth, I actually get 27.7 years. So that's quite a while. 27 years. None of you are 27 years old. So that's quite a while that it would take before this investment would reach that $10,000 mark. I'm sorry, I'm off on one of my slides. Not 27.7, 23.3. We'll have 27.7 in a minute to an answer. I need to mark my page a little bit better. 23.3. Yeah, there we go. Okay, I have one more question associated with the content here. That question has to do with keeping parts of this the same again and changing parts of it. So here's my question. How much would have needed to be invested for 5 years at 4.5% compounded continuously if $5,000 was needed at that time? So again, thinking about my formula, A equals P e to the RT. I want $5,000. My question's asking me how much would my initial investment need to be. So I don't know that it's $3,500 in this particular part of the question. It's asking me what that would need to be instead. It's telling me that I do have the same interest rate, and I'm dealing with still a 5-year time span that I'm looking at. So this is what I end up having. So we have $5,000 equals P e to the, and if you want to, it might be easier sometimes to go ahead and simplify like that exponent, for example. That's 0.225. Now, if you'll notice, this e to the 0.225 is actually multiplied by p, so if I need to solve for p, I would divide by it. So this is e to the 0.225 on both sides. So this piece cancels, all I'm left with is p, and if I take my calculator and I take 5,000 divided by e to the 0.225, I end up with 39.9258. And usually, money, we're going to do to 2 decimal places. Sometimes they might have you round money to a nearest whole number, but for the most part, 2 decimal places of money is quite realistic. Okay, so many of you are interested in the sciences. You're in chemistry right now, I know everyone. So let's take a look at a couple of examples that are not necessarily related to interest, money kinds of computations, but to a science kind of experiment. This one's a biologist. A biologist has a 377-gram radioactive substance. Find the mass after 6 hours if it decreases as continuous exponential decay by 7% per hour. Okay, so there's some key words in here that are super important. Continuous exponential decay. That actually is telling you you have this continuous interest rate type problem. It's compounding, or it's decreasing in this case. It's decaying continuously. So this is the right place to start. Now it tells us that we have a 377-gram substance, so that's the initial amount. It's also telling us that it's decaying at a rate. Well, decaying means that the rate's negative, and it says it's by 7% per hour, 0.07, right? So 7%, and it's negative because it's decaying, would look like this. And it tells us that we're going to do this for 6 hours. So in this case, right, like the t is not numbers of days, it's numbers of hours, and that's totally okay. If you plug that into your calculator and simplify, you will end up having 247.7 grams. Okay, but the key word is super important. The fact that it's actually growing in that way. Okay, so the next one is an interesting question about doubling. It's posed into a context of kind of like it's money, but it doesn't actually have anything specific to do with money. So it says the amount invested in an account increases, and it gives you an equation, y equals y0, e to the 0.25t. It does tell you y0 is the initial amount invested, much like the p in the principle that we were looking at. And it wants to know how long will it take the initial amount to double. So there's actually nothing here about money, right? I mean, we've got a formula, and we want to know how long it takes for whatever is happening to double. So here's where we're starting with, y equals y0, e to the 0.025t. Okay, so here's what you need to know. Y sub 0, this notation is not a 0. It's just saying that it's not the same as y. There's two different values. It's kind of like when we do y sub 1 in the slope formula or something like that. Okay, so these are just two different y values. Y0 is the initial amount and y is the secondary amount. So the thing is, you can actually choose any initial amount you want, as long as when you do the secondary amount, like the y value, that you double it. So I tend to use 1 and 2, right? If I start with 1, I have 2. That's doubled. You can use whatever you'd like. 1 just ends up being really nice because if I multiply 1 by anything, I don't end up having to divide by anything first. It's already a 1, okay? So we're going to solve this just like we did before with logarithms. We'll take the natural log of both sides. So natural log of 2 equals the natural log of e to the 0.025t. The natural log of e is eliminated, and I'm left with the 0.025t. And I will divide by 0.025. Of course, that cancels this part. I'm left with my t value, and t would end up being 27.7. See, that's the number I tried to tell you earlier on that previous problem when I lost my place. 27.7 years. And again, rounding to the nearest tenth is what most of the problems in this particular problem set have done. So this is what I was doing on this problem. 27.7 years for this value to double. It's a really long time, right? 27 years. All right, last example. All right, we have a mass of a substance following a continuous exponential growth model. Okay, so that continuous exponential growth model, that tells you it's A equals P e to the RT. If it didn't have that phrase, we'd be using the other formula, the A equals P1 plus R over N to the NT. It says it's found to double every 19 minutes. Okay, so there's that doubling feature again we just mentioned. There were 58.9 milligrams to begin with. So after 19 more minutes, it's going to have twice that much, right? And then another 19 minutes later than that, it's going to have double that amount. And it's going to keep doubling every 19 minutes. So the question on part A wants us to create an equation relating the amount of the substance at the time from the beginning of the experiment. So if you take a look, we've got this equation, A equals P e to the RT, and we want to know what each of these pieces are. Now we know eventually that the P is going to be the 58.9. But if I put that in, I'm going to put it in over here because we will need it eventually. Actually, you know what? We'll go ahead and do that. This will be my final equation over here in a moment. But what you need to notice is that we don't know R, right? It doesn't tell us the rate. It doesn't exactly tell us the time, but it does give us some information that relates the time to a specific amount. In particular, it tells us that after 19 minutes, the amount doubles. So if you'd like to take 58.9 and double it, you'll get 117.8. So what I know is that there's 117.8 after it started at 58.9, and that happens after 19 minutes. So the first thing to do is to divide by the 58.9, and hopefully you know exactly what that will be because we just used it to find the 117.8. 117.8 divided by 58.9 is 2, right? So we could have just chosen numbers 1 and 2 instead of 58.9 and 117.8. It would have worked the same way. And then we have the natural log to take on both sides. So the natural log of 2 equals the natural log of e to the 19r. Natural log of e is 1. So I end up being left with, hang on, let me move this down a little bit, with r equals, 19r equals the natural log of 2. And then I would divide by 19. So when we're working on the problems like at this point, your questions in your book are going to say things like don't round and enter any intermediate steps. And the whole point is they don't want you to lose accuracy, and I don't want you to lose accuracy either, but it's going to make a whole lot more sense if we use some sense of rounding. So if it tells you don't round in intermediate steps on this particular value and finding r, I'm going to tell you you can round, and let's just keep 4 decimal places, okay? So if I were to divide natural log of 2 divided by 19, I'm actually going to get 0.0365. So my equation that I've been trying to create, I can do that now, because now I have the initial amount here, right? And I have the r value that I didn't know before. So my equation ends up being A equals 58.9 e to the 0.0365t. And that would be the equation that I'm actually asked to find in this part of the problem. And then what I'm asked to do in part B is to actually use that equation I created. I don't know where that slide went, but I'll write it in for you. To use that equation that I created to actually find out how much is going to be present in 5 minutes. Let me write that question out. You can at least get a better backdrop, I think. Hang on. We'll go with that, just for fun. Okay, so part B was supposed to say, again, don't know where the slide went, but part B, how much will be present after 5 minutes. All right, so we had A equals 58.9 e to the 0.0365 times 5 for 5 minutes. And if I simplify all that, I end up getting, and again, we'll use 1/10 or tenths place. This would be 70.7 milligrams. All right, so remember, this lesson, along with, this is going to be homework number 26. Homework number 26, along with homework 25 from yesterday, are both going to be due when you come back after Thanksgiving. I am not recording anything for Friday. You have Friday off as far as new material to cover. It's just those 2 lessons over the break. Have a lovely break.